Hey students, I thought I'd make a video here of the two harder ones. Let me start with this hard one. It's our last chapter of this semester, chapter 17, and it's actually also chapter 17 from the harder book, University of Physics, and it's number 137. So I printed it up here, and then I also printed up a little section out of your textbook. This is not from the hard textbook. This is from the college physics textbook. But it talks about what observed frequency you would have when the source is moving and what observed frequency you would hear when the observer is moving. This is called the Doppler effect. And that's what this problem centers around here. And so it says a stationary observer. Okay, so not this one here, but this one here for a stationary observer. Stationary observer hears a frequency of 1,000. So this is what they hear. This is what they observe. This would go right here. As the source approaches, okay? And so they don't tell us what the frequency is. They just say it is approaching, okay? Now, over here, it says the frequency is 850 hertz when it departs, okay? So, again, same formula, if you will. And this 850, though, is also going to go right there. But there's going to be a difference between this plus and this minus. And we use the plus sign down here when they are moving apart. And we use the minus sign when they're coming together. So I guess it would look something like this. Although I better keep reading on here. It says the source moves at a constant velocity of 75 miles per hour. So I suppose we better watch our units here. What is the temperature? And so we also know that velocity of the wave is dependent on temperature. So that's going to be the key recipe here. So let me give it a try for the first one. As they're approaching each other, we're going to get 1,000 hertz that the observer is hearing. A stationary observer hears a frequency of 1,000. What we don't know is the actual velocity, the actual frequency. We also do not know the velocity of the wave. And so these are the two unknowns. But we do know that they are coming together. Let's see. Do they give the plus minus along a line joining the source and the observer's speed of sound? There we go. The minus sign is used with the motion towards the observer. So that's what we have here first. So it's minus this 75 miles an hour. Well, maybe I better find a, well, I'll just do it right here. 75 miles per hour. And do a little bit of unit conversion here. So we know that there is so many meters in a mile. And so going way back to chapter 1, I would put 1 mile has 1,609 meters in it. And then also to get rid of hours, I'll put it on the top and seconds down here. And so 1 hour has 3,600 seconds. That's because you'd go 60 times 60. And so 6 squared is 36 and 2 zeros. So hours would go away, miles would go away, and you would end up with meters per second. So grabbing a calculator, I'm going to go 75 times 1,609. And divide by 3,600, and we're looking at about 33.5 meters per second. So 33.5 would go right there, okay? So that's the first equation, if you will. Now, repeating this for when the source now departs, and so they kind of maybe cross paths, or well, this one, so here's the observer stationary, okay, and then the source goes by and past it. And so you're going to get 850 for the frequency that the observer hears. And then you have the frequency of the source, the velocity of the wave, divided by the velocity of the wave. But this time it's plus 33.5. Okay, because somewhere in here it'll say the plus sign for motion away from the observer. All right, so these are our two system of equations, and there's two unknowns. One is the frequency of the original source, and one is the velocity of the wave. Now, we really only care about the velocity of the wave because that is going to lead to the temperature. So I might not even bother to solve for the source. In fact, I'll just do kind of a fun quotient, that is divide one equation by the other. That is, if I take this top equation and divide it by 850, which is that one, I will get, and I'll just write it down here, 1,000 over 850 equal, let me just rewrite the numerator here, and then divide by that 850, but this time the 850, I will do a substitution of what the 850 is equal to. And so that was kind of my phrase of just take one equation and divide by the other. So I have the two numbers on top of each other, and then I also have the two formulae on top of each other. But what's really nice, and this is kind of what I saw coming, and I go, okay, this would be a great way to get rid of, mathematically, get rid of that variable. And then I'll be left with an equation that only has the velocity of the wave, which looks like I've got quite a few steps of mathematics still to do, but at least it's only one variable, and I can solve that. Now, maybe I'll make one more line before I go to a new piece of paper here, but this is a compound fraction. And so if I take the numerator and then leave it alone and then flip and multiply, I'll get this, which is very helpful because one of those cancels off and making it a little bit easier. Okay, so what I have over here is 1,000 divided by 850. And why don't I just make a number out of that? And so that is 1.18. So maybe I'll put here page 2, 1.18. And then that would equal to the velocity of the wave plus 33.5 over the velocity of the wave minus 33.5. And then when I bring this to the other side, I get 1.18 times the velocity of the wave minus 33.5, and then the velocity of the wave plus 33.5. Do the distributive property, 1.8 velocity of wave minus, let me do that number. So times 33.5, and then this becomes 39.4 equals the velocity of the wave plus 33.5. Now, if I can do two steps, hope this doesn't do too much math, but I can bring this over, which now makes it a -1. Taking it away from them leaves me with 0.18 velocity of the wave. And then bringing this over would add it together. And so that's a 9, 12, carry a 1, 672. And so the velocity of the wave would then be 72.9 divided by 0.18. And so we're looking at about 400, and 5 meters per second. Wow. Which, by the way, is a pretty fast speed, because we said that at room temperature, it's 344, and at 0 degrees Celsius, it's 331. In fact, the little formula we have for the velocity of the sound waves in air, maybe I better come back to here. I think they're kind of implying in the air, a stationary observer hears. So they didn't directly say the observer was a human in the air, but I'm going to assume it's not a dolphin or something underwater here. And it's okay, it's in the air. And so then we have that 331 times the square root of the temperature on the Kelvin scale times 273. Actually, is that how you guys write it? I usually write it a little different. Actually, let me just think I have section 2 in the book close by. Yeah, they list a lot of different ones. Yeah, that's how they list it. Good. And then they say this has to be on the Kelvin scale. And I'm a little more familiar with it listed on the Celsius scale. But I like this one. It's a simpler formula. Okay, so now I can put in my 405 for the velocity I get, the 331, and then the square root of t over 273. And maybe then the first thing I'll do is to take the 405 and divide it by the 331, and that gives me about a 1.22. Then I'll square both sides, so this becomes about a 1.50 temperature over 273. And finally, I get the temperature, although it is in Kelvin, would be that number times 273. And so we're looking at about 408.7. And just to see what it is on the Celsius scale, we're looking at 136-ish degrees Celsius. All right. Was there a part B? No. Okay. So, good problem. Hope that helps. All right. Take care.